Now, there are various devices that could be used. One of the proposals is for a Respirocyte. We saw the video earlier this morning of a Respirocyte providing oxygen, and the basic concept is fairly straightforward. This is a device which would have oxygen under fairly high pressure, 1,000 atmospheres, and it would dispense the oxygen in a controlled fashion while it was circulating through the bloodstream. It would also have the ability to take up carbon dioxide, and in combination, those two abilities would allow this device to sustain our metabolism, to sustain our breathing, essentially, even if you were not breathing, and even if your circulation had stopped. I believe the reference this morning was to sitting at the bottom of a pool for a few hours. More usefully, you might have this in your body if you were prone to heart attacks, at which point, if you had a heart attack, you would then call the emergency room and say, I had a heart attack, what should I do? As opposed to falling over because you were unconscious. Second device is a microbovore. This is the device which could clear out pathogens from the circulatory system very rapidly. It has an intake, it has robotic arms sticking up that wave around, and they have on their tips, they have binding sites that would bind to specific antigens that would be present on whatever pathogen was causing the problems, and you would then sweep the pathogen into the maw of the device where it would then be digested. We also have the Chromalocyte. The Chromalocyte is a device which would be able to provide individual substitution of the chromosomal material inside an individual cell. In operation, these devices are going to be more sophisticated, and to use them, you would probably require a complete navigational chart of the human body. In other words, as a preliminary step in the use of this device, the first thing you would do would be to map out the entire structure of the body accurately down to the level of individual cells. So this would require a network of small nanorobotic devices operating to gather information and provide a detailed description, and then provide a route so that each of these devices could then go to a specific assigned cell, remove the chromosomal material that was present, and replace it with a new set of chromosomes which were correct, did not have errors, did not have epigenetic errors, etc., etc., etc. So this should allow us to deal with a range of problems. Of the three devices I've described, this is probably the most complex and will take the longest time to develop, but all three are enabled by the core capabilities of a nanofactory. So how do we get there from here? So the claim I'm making is medical nanorobots can keep you alive and healthy. Nanofactories can manufacture medical nanorobots, so we need a nanofactory. How do we build a nanofactory? We have a plan. Basically, we are today in this dot on the left, and the dot on the left represents all the experimental capabilities that we have at the moment. And as time goes by, we see experimental progress moving in various directions, some of it moving in the direction of molecular manufacturing, some of it moving in other unrelated directions. And eventually we'll get to this large gray oval, which has been labeled core molecular manufacturing capabilities. And this is a set of capabilities that will let us build a whole range of things, including specifically medical nanodevices. And what we're proposing to do, and what we are pursuing, is a plan to go directly to a set of capabilities which will then allow us to manufacture the medical nanodevices, and which will also enable an explosion of other capabilities. This is the direct route. Now, this can be contrasted with the sort of business as usual route. This is the route of, well, sort of standard scientific research. As we all know, scientists wish to be funded, they wish to pursue what they want to pursue, and they don't want to be inhibited about that. And the usual argument is we don't know what we're going to discover until we discover it. And this concept leads to the embrace of random directions and random goals. So the concept, even the concept of long-term directed, goal-directed development is a difficult one to convey, and you often see people wandering about in random directions, and maybe that will eventually reach something useful, and maybe it won't. But if we want to have the medical capabilities developed in a timely fashion, we're going to have to do something a bit more directed. To give you another feeling for this, if we're on an exponential trend towards medical nanofactories and indeed nanotechnology in general, then one can imagine, say, 2 exponential lines going upwards. And at the beginning, when you're starting out, the difference between 2 of these lines is relatively small, which translates into relatively modest resources. So at the beginning, as you start, you can say, wait a minute, I want to be on the faster schedule. Let's spend more money and get up to the faster schedule. And as time goes by, you find that having started that exponential trend more rapidly, you have reached the goal substantially faster. Whereas if at the beginning you don't spend the money, then it's still an exponential trend, but exponential trends take off at their own pace. If you're on the lower curve, you're now going to take a longer time, and because of modest resources that were not available here, you get a long delay there. And that is, of course, very important to us for a very simple reason. We would like to have this technology developed during our expected lifespan. This would be useful. If it is developed following our lifespan, yes, it will advance science and benefit the children and It would not have a great benefit for us. Well, how do we do this? Basically, it looks as though this kind of thing, or the development of a nanofactory, is going to take, if we follow the direct path, if we actually pursue this in a directed fashion, will take about 20 years. And probably something like $1 billion. The good news, though, is you don't spend all the money up front. It looks as though if we start out spending on the order of $1 million, and then every 2 years double that amount, that we should be able to maintain the schedule and eventually wind up in year 20 with all of these capabilities. And just out of curiosity, how many of you expect to be alive and healthy in 20 years? Everybody, pretty much everyone. 40 years. 60 years. Ah, okay. Yes, you're already taking into account the fact that technology is advancing. Well, we better get this rolling, because how do I phrase it? We don't want any slippage in the schedule on this one. So that's what I had to say. And now, questions. How much time have we got for the questions?